Hello everyone, myself Dr. Shaibi, working as Assistant Professor in Cape Institute of Engineering and Technology, Coimbatore. In this video, we are going to solve the system of congruence equations using the Chinese Remainder Theorem. Today, we are going to have two different kind of problems, whereas in the first problem, it has the moduli numbers as a pairwise relatively prime, whereas in the second problem, the moduli are not pairwise relatively prime. Now let us look into it. What is Chinese Remainder Theorem? It is a fundamental result in the number theory that helps to solve systems of simultaneous congruences with different moduli. Now, let us have m1, m2, etc. mn be a pairwise co-prime positive integers. That is, the GCD of mi and mj should be equal to 1 for different I and j. Then, this system of congruences should have a unique solution modulo of capital M. This capital M is nothing but the product of these moduli. And the general solution of this congruence equation is x is equal to summation of ai, mi and yi modulo m, where m is the product of those moduli, capital Mi is m by mi, and yi is congruent to mi inverse modulo small mi. So these are all steps that we have to follow to solve this system of congruence equation. Let us first compute m, where m is the product of mi's and we have to find mi. It should be m by mi. And then we have to compute the values for yi, where this yi is found by using this congruence expression. Mi into yi is congruent to 1 modulo mi. And finally, after computing this mi and yi, we have to frame this expression where this is the solution for the given system of congruence expression. Now let us understand this concept thoroughly through a problem. Now let us have a 3 system of congruence expression. So x is congruent to 2 modulo 3, x is congruent to 3 modulo 4, x is congruent to 1 modulo 5. So here a1 is 2, a2 is 3, a3 is 1, and small m1 is 3, m2 is 4, and m3 is 5. As I said before, first we have to find the value of capital M. This capital M is nothing but the product of these moduli numbers 3, 4 and 5. So M is equal to 3 into 4 into 5, it is 60. Now we have to find 3 capital Mi, that is Mi equal to M by Mi, which means we have to find M1, M2 and M3. So M1 is equal to M by M1. So it is equal to 60 by 3 is 20, and for M2 it is 60 by 4 it is 15, and M3 is 60 by 5 it is 12. So after finding this M1, M2, M3, we have to find the values for Y1. So this expression can be rewritten as M1 into Y1 is congruent to 1 modulo M1. Now, just now we found the answer for M1. M1 is 20. Now substitute in this expression. So 20 into Y1 is congruent to 1 modulo 3. Now this expression can be rewritten as 20 into Y1 minus 1 by 3. Now our aim is to find the value of this Y1. We have to substitute the values of Y1 in such a way that this expression has to be satisfied. Always we have to start with 1 and we should end with this modulo number. So here we have 3. So we have 3 different cases to substitute in this expression. So y1 is 1 and y1 is 2 and y1 is 3. So we can substitute for 3 different cases of y1. So definitely for a particular number, this expression will be satisfied. Now let us check for each y1. Now let us take y1 as 1. So if I substitute y1 as 1, it becomes 20 times of 1 minus 1 by 3. It is 19 by 3. So this is not satisfied. Now let us take y1 as 2. 20 times of 2 minus 1 by 3. It is 40 minus 1 by 3 is 39 by 3. So this expression is satisfied if I take y1 as 2. So the value of y1 is 2. Now let us solve like the same procedure for finding y2 and y3. So this expression can be rewritten as m2 into y2 is congruent to 1 modulo m2. And we know m2 is 15. So 15 into y2 is congruent to 1 modulo 4. Let us rewrite this expression. It can be rewritten as 15 into y2 minus 1 by 4. As I told you before, we have to find the value of y2, and this can be done by substituting the values from 1 to the maximum of this modulo number 4. So I am starting to solve by substituting y2 as 1. So it is 15 times of 1 minus 1 by 4. It is 14 by 4. It is not satisfied. Now let us substitute for y2 as 2. 15 times of 2 minus 1 by 4. It is 30 minus 1 by 4. It is not satisfied because it is 39 by 4. Now let us substitute for y2 as 3. 15 times of 3 minus 1 by 4. So it is 15 3 is 45. 45 minus 1 is 44 by 4. Yes, it is satisfied. So the value of y2 is 3. Now let us do the same for finding y3. So the expression is m3 into y3 is congruent to 1 modulo 5. Now this expression can be rewritten as the previous one. So it is 12 times y3 minus 1 by 5. So here the modulo number is 5. So we have to substitute from 1 to 5. So now let us start from 1 for y3. If I substitute y3 as 1, it becomes 12 times 1 minus 1 by 5. It is 11 by 5. It is not satisfied. Now y3 as 2. 12 times 2 minus 1 by 5. It is 24 minus 1, which means 23 by 5. It is not satisfied. Now y3 as 3. 12 times 3 minus 1, which means it is 36. Minus 1 means 35 by 5. Yes, it is satisfied. So after finding the values of y1, y2, y3, we are going to frame the unique solution for the given problem. So x is equal to a1 into m1 into y1 plus a2 into m2 into y2 plus a3 into m3 into y3. So this expression should be solved, and it is 251. And after getting the answer, this final answer should be the remainder of taking modulo 60. And if I divide this 251 by 60, the remainder which I am getting is 11. So x is congruent to 11 mod 60. So this is the final unique solution for the given system of congruences. And this expression can be reframed as x is equal to 60 times t plus the remainder 11. Now the given problem has many solutions if I take many values for t. So if t equal to 0, this expression x is equal to 11. And if I take t is equal to 1, this expression would be 71. So for many t's, I have written so many solutions. So these numbers will satisfy the given congruent equations. Now let us check whether the answer we found is correct or not. So I am going to substitute this answer 11 in the given congruent equation. So I am just taking the first congruence expression. X is congruent to 2 mod 3. Substitute x as 11. So it becomes 11 congruent to 2 mod 3. This expression can be rewritten as 11 minus 2 by 3. So it is 9 by 3. Yes, definitely it is satisfied. So similarly, you can check the same scenario for the remaining two congruence expressions. So this is the solution for the given problem. Now let us move on to another problem where in the situation the moduli number are not relatively prime. So what happens in that scenario? Now let us take two system of congruence expression where the moduli number are not pairwise relatively prime. So in that case, the solution would be exist if the GCD of mi and mj should divides this ai minus aj, and this condition should be satisfied for any pair of I comma j. And if this condition fails for at least one pair, then the given congruence expression does not have solution. So now let us learn this concept more deeply with the help of an example. Now let us take two congruence expression. X is congruent to 3 mod 6. X is congruent to 5 mod 10. Here A1 is 3 and M1 is 6. A2 5, M2 is 10. Now before solving this, we should know whether this congruence expression have a solution or not. So to check whether this expression have a solution, let us take the GCD of those moduli 6 and 10. The GCD is 2 and this 2 should divide the difference of this 3 and 5. So 3 minus 5 is minus 2. 2 definitely divides this minus 2, which means this congruence expression has the solution. Now let us find the solution. So for this kind of problem, the methodology differs. So we have to take the first congruence expression, x is congruent to 3 mod 6. So here this expression can be rewritten as x equal to 6 times plus the remainder 3. So this expression is rewritten as x is equal to 6 times k plus 3. Now after finding the first expression for x, we have to substitute that x in the second expression. So here we have x is congruent to 5 mod 10. So substitute that x in this x place. So 6k plus 3 is congruent to 5 mod 10. Now this take this 3 to the right hand side. So 5 minus 3 is 2. And this expression becomes 6k is congruent to 2 mod 10. So here we can observe that here these two numbers are multiply of 2. So let us divide these two numbers with 2. So the reduced expression is 3k is congruent to 1 mod 5. So here we want to find the inverse of the number 3 using this expression 3k minus 1 by 5. So to find the inverse, we have to use the same methodology what we have followed in the previous problem. So here if we have to substitute from 1 to the maximum number of 5. So if I substitute k as 1, it becomes 3 minus 1, which means 2. 2 is not divisible by 5. Now let us take k is equal to 2. So 3 times 2 minus 1, it means 6 minus 1, which is 5. So 5 is definitely divisible by 5. So let us take the final answer for k as 2. So k is congruent to 2 mod 5. So after finding the solution, you have to reframe this expression as 5 times m plus the remainder 2. After finding this expression for k, we have started for x as 6k plus 3. We have to substitute the value of k in the first expression of x. So taking the value of k and substitute in the place of k. So x is equal to k times 6 times k plus 3. Substitute k as 5 times m plus 2. So after solving, I will be getting 30 times m plus 15. So this 30 times m is nothing but it is a modulo number. And this 15 is a remainder. So x is congruent to 15 modulo 30. And this is the set of all integer solution for the given set of congruences. Now let us check whether this 15 is a solution of the given problem. So let us take 15 and substitute in the given problem. So the given first congruence expression is x is congruent to 3 mod 6. Substitute x as 15. So this expression can be rewritten as 15 minus 3 by 6. Obviously it is 12 by 6. Yes, it is divisible by 6. So this 15 is a solution of the given problem. So similarly, you can check for the another congruence expression. So here also we can definitely check the given 15 as a solution for this congruence expression. So finally, for this expression, 15 is the solution. Okay, so I hope now you can able to solve this system of congruence expression by understanding the concept much easier. I hope you enjoy this video. Thank you. we will meet again back in the next video.